Howdy. Today we're going to dig into one of the most fascinating areas of mathematics, and also very useful areas. You're relying on it right now, whether you know it or not, and it's something which is very simple, but also very deep problems that are hard to solve. So let me show you what I'm talking about here. So suppose I give you this many objects. And I ask you to put those into even piles. Put them evenly into piles. The question is, could you do it? And I think you probably could without too much trouble. There's a couple piles that have the same number. Here's another way to do it. I could put them into piles like this. And I would have this many piles. And notice I'm not even using numbers here. I'm just looking at it without even using numbers and just saying, sure enough, we can put it into piles. Okay? What happens if I include one more and I want you to put that many things evenly into piles? Could you do that? And I think no matter how hard you try, you discover it's impossible. You could try all possible combinations and you'd be frustrated. The only option you would have would be one pile with all of them, like that, or a pile for each one. Okay? You could do it like that. But other than those two cases, which will always be possible, you can't break it up evenly into piles that don't have either the whole thing or one of each. And that's why we call this many things, and how many are there? We use the English numbers 1, 2, 3, 4, 5, 6, 7. We say that 7 is a prime number. Any number in which you cannot break it up into even piles like that, divide it up into even piles evenly, is called a prime number. So your prime numbers, let's list off the ones that we know. Some of the ones we know. 2 is the first one. 1 is just all by itself. It just kind of it can't be broken up at all because you just have one thing. But 2 can't be broken up into other things. 3 can't. 4 can, right? You can take this many things and break it up into even piles, but 5 can't. 6 we just saw could. 7 can't be broken up. 8 you can. 9 can be broken up into piles of 3. 10 can be broken up into 2 piles of 5 or 5 piles of 2. 11 can't be broken up. 12 can be broken up lots of different ways. 13, 15 can be broken up into 5 piles of 3 or 3 piles of 5. 17, 19, not 21. 21 can be broken up into 3 piles of 7 or 7 piles of 3. 23, 25, 27, 29, 31, 33, 35, 37, 39, 41, 43, and it just keeps going. Okay? Keeps on going. The question is, does it go forever or not? We're going to talk about that. So those are all called prime numbers. If a number is not prime, then as we say, if it's not prime, that's because it can be divided up into prime numbers. And so since it's broken up into different numbers, we call it composite. Okay? Composite numbers. So all the other ones are composite. 4, 6, 8, 10, 12, 14, 15, 16, 18, 20, and so on. Okay? Those are all composite. And as I say, if it is not prime, then we can break it up. So let's take some and see once how we can indeed break them up. Let's start with 60. If you take 60 and divide it by 2, you get 30. If you divide 30 by 2, you get 15. If you divide 15 by 3, you get 5. So the composite number 60 can be written as 2 times 2 times 3 times 5. Notice that? So we can break it up into its factors, into a product of its factors. And what's important is it doesn't matter how I do it. If I took 60 and first divided it by 3, say, then I would get what? 20. I could take 20 and divide it by 5, and then I would get 4 and take 4 and divide it by 2, and I end up with exactly the same thing. See that? It doesn't matter what order you do it, you end up with the same factors. So that's key. Okay? Let's try several of these just so you get the hang of it. Let's try 70. Okay, take 70 and divide that by 2, and we get what? 35. Divide 35 by 5, and you get 7. So 70 is equal to 2 times 3, I'm sorry, 2 times 5 times 7. Okay, let's try another one. I'll put them all down here so I don't have to keep looking down all the time. 82 I want. And 90, 165. 504 and 720. Okay, and feel free to stop the video and try these on your own. Okay, here's 82. If I take 82 and divide it by 2, I get 41. Can 41 be divided by anything more? Nope, that's a prime number. So 82 is just 2 times 41 as an example. If I take 90, what's that going to be? 2, and we get what? 45. I could divide 45 by 9, but I don't want to do that. I want these to all be prime numbers. So I'll divide it by 5 and get a 9 up here. Then get 3 and a 3. And I always like to, again, I can put them in any order. I like to start with the smallest. So I'm going to write 2 times 3 times 3 times 5. See how that works? How about 165? 165, let's see, let's divide it by 3. 3 goes in there 5 times, then you get another 15 here. 3 goes into that 5 times. Now I can divide that by 5 and get 11. So 165 is 3 times 5 times 11. See that? How about 504? Divide by 2. 2 goes into this 25 times, and then goes into 4 2 times. Now I can divide that by 2. It goes in 12 times, left of 12. Goes into 12 6 times. Divide by 2 again, I get 63. Divide by 3, I get 21. Divide by 3, and I get 7. So 2 times 2 times 2 times 3 times 3 times 7. Okay, look at there. Try one more. 702. Try it on your own if you haven't done them yet. 2 and you get 360. 2 and you get 180. 2 and you get 90. 2 and you get 45. 3 and you get 15. 3 and you get 5. So look at all the 2's. I could write that as 2 to the 4th, but I'll just multiply it all out here. 2, 2, 2, 2, 3, 3, and 5. So even with small prime numbers, if you use enough of the factors together, you can get some pretty big numbers, obviously. Okay? So the fundamental theorem of arithmetic states just exactly what we discovered here. That you give me any composite number, and any composite number has a unique way, one and only one way, of being divided up into its prime factors. Okay, that's an important fact. So important that we call it the fundamental theorem of arithmetic. Every area of mathematics has its own fundamental theorem. There's a fundamental theorem of algebra, and the fundamental theorem of calculus. I think there's probably some other ones as well. Those are the ones that come to mind. Okay, so now I want to talk about something else, which I'm just going to call this a fact, and see if you agree with me on it. Let's take the first 2 prime numbers here, 2 times 3, and then we'll add 1 to it and get 7. Okay, now notice if I took 2 times 3 without the 1, I would get 6. 6 divided by 3 is 2. 6 divided by 2 is 3. So what happens if I take 7 and divide it by 2? Well, I'm still going to get that same 3 I did before, but that's only going to give me 6, and I'm going to get a remainder of 1. See that? So the point is, my 7 here cannot be evenly divided by 2 because I'll get a remainder of 1. Similarly, if I take my 7 and divide it by, what did I divide that by? 2? Now I'll divide it by 3. If I divide it by 3, I'll get 2 here. That'll give me 6, and again I'll get my remainder of 1. So the point is, these two things give me a number which can be evenly divided by both of them. As soon as I add 1, then this number can't, because when I divide it by this, I'll get this with a remainder of 1. And I don't have to stop with just 2 times 3. I can go 2 times 3 times 5, for example, plus 1. What does that give me? That 6 times 5 is 30, plus 1 is 31. So again, 2 times 3 times 5, that gives me 30. 30 can be divided by 5. It'll give me 6 with 6. It can be divided by 3. It'll give me 10. It can be divided by 2. It'll give me 15. So 30 can be divided by any of these, and if you divide by 1, you're going to get this as the result. As soon as I add 1, then the same thing happens as before. I get my 31 and I divide it by 3, and what am I going to get? I'm going to get 10, which is this times this, and that gives me 30, and then what am I left with? A remainder of 1. And it doesn't matter which one I divide it by 5. Let's just go ahead and do it. If I take 31 and divide it by 5, I'm going to get 6 with a remainder of 1. If I divide it by 2, I'll get 15, which is this times this, with a remainder of 1. Okay? And you don't even have to stop there. You can go as far as you want. Do you agree? If I multiply this by 7 and add 1, I'm going to be at what? 30 times 7 is 210, plus 1 is 211. So there's 211, and so I take 211 and divide it by whatever you please. Divide it by 5. What am I going to get? If I divide it by 5, I'm going to get 6 times 7. I'm going to get 42, and that gives me 210. And what do you expect again? I have a remainder of 1. So you take a bunch of numbers together, multiply them together, and add 1. And whatever this number is can't be divided evenly by any of these, because why did we construct it this way? Because you're going to get a remainder of 1. Okay, so that's just a fact. Okay, so I'm going to write it down like this. I'm going to write 2 times 3 times 5 times 7 times 11 times 13, all the way up to wherever you want to go. I'll say times 43 plus 1 cannot be divided evenly by any of those primes, 2 through 43. Okay? Why? Because of the way we constructed it, it can't be. Okay, very good. So that is just an important fact which leads us to be able to answer this question. How many primes are there? Okay? The most important sub-question here is, are there a finite number of primes, or are there an infinite number of primes? Do the primes just keep going on and on and on forever, or at some point do they stop? Okay, notice that they become more and more sparse as you go. Here they're really concentrated together, and then even as we go out in this table, notice that now we have jumps of 4, and here's a jump of 6, and so on. So they get more and more sparse as you go, which makes sense because there's more and more numbers that can divide into them, right? It's harder and harder to choose a number which none of these other ones divide into, so they become more and more sparse. So the question is, at some point, do they become so sparse that there just aren't any more? Or do they keep continuing even though they get more and more thinned out as you go? And this question was asked and answered by one of the great mathematicians way back about 2,500 years ago, Euclid. Euclid provided a proof, and he proved that there are an infinite number of primes. They never stop. They never stop. And I think his proof is maybe the most beautiful proof in all of mathematics, because it's fairly simple, and yet it's also very powerful. It tells us something very, very important. Okay? We'll see why this is important. In fact, let me tell you right now why this is important. It turns out that in order to encrypt information such as your credit card number and anything having to do with your computer, all those things are encrypted, which is a mathematical term for finding ways to send information secretly so that people can't dig into it and find out the information. Just a day or so ago, yesterday in fact, I heard that someone broke into the Twitter account and found a way to break in and send Twitter messages that seemingly came from Obama and from Biden and from, who else was it? Oh, Warren Buffett. I mean, some big names. And so normally when this sort of stuff happens, it's because people are breaking in and finding ways to break in. And so this is what prime numbers are important for. And here's why. Suppose you take two prime numbers. Say I don't have one here on the top of my head, but say, for example, say that happens to be a prime number, okay? Now, I'm sure that computers use ones much bigger than that yet, but a big prime number. So we know it, and once we have that number, you and I, if we both have that number, we can take that number and we can multiply it by other things. Like we can multiply it by 29, okay? Yeah, or you'd multiply it by yet even another big prime number. You'd multiply them together. And then I would send this information to you, which is this great big number, and you know this one, so you would take the result and you would divide it by this, and you would get the result. And now this result would give you some information. If it's a 29, I might say, go ahead and buy some more stock in Apple or something like that. So the point is, by knowing what this big prime number is, you and I can send information out. Other people who don't know it can't use it, and but those of us who do, we can divide by it and get this information out. That's just really roughly the idea. So the point is, these prime numbers are needed for any time you're trying to keep things secret, which I understand that every computer, if I understand this right, every computer has its own prime number associated with it. So in order to be able to do that, you have to know you have a lot of prime numbers to choose from. Infinite is enough. And also that they get arbitrarily big. And so if they're an infinite number, then they're going to get bigger and bigger and bigger as they go. So this is very important in order to be able to even exist in our modern culture, okay? So it's important stuff. So anyway, let me prove to you why there are, in fact, an infinite number of primes, okay? And here's what you do. You say, suppose not. Suppose that n is the largest prime. Okay? Kind of like what a lawyer might do in court. Say, I'm going to prove that you were there on the night of the murder. Because suppose you weren't there. If you weren't there, then da-da-da-da-da-da. So we're going to do something similar. We're going to say, hey, suppose that there is a largest prime, and we're going to call it n. Okay? Just suppose. So if there is, then here's what we can do. We can take all the prime numbers and multiply them together. All the way out, going far past 43 obviously, all the way out, and the very last one is n. Okay, multiply them all together, and then, can you see what's going to happen? I'm going to make sure my computer is still working. Okay, yep, still working, very good. Okay, so we're going to take them all, and then once we have them all, we're going to add 1 to it. Just like I did right here, we're going to add 1. And this is our new number. Let's just call it, let's call it P, for possible prime. Or just for P, we'll just call it P. Okay? So, are you with me so far? We're claiming that n is the biggest prime. Once you have n, you multiply all the primes together. Don't leave any of them out, all the way up to n. N is the last one, and then you add 1 to it. And now you got yourself a bigger number P. Now, do you agree with me that one of two things is true? P is prime, or P is not prime. Agree? It's either a prime or a composite. One of those two is true. If P is prime, then do you agree that P is a much, much bigger number than n, because you took n and multiplied by all these and added 1. So if P is a prime number, then obviously n was not the largest prime, because P is prime and P is much bigger. So then n is not largest prime. Okay? What if P is not prime? Okay? If P is not prime, then what does it mean to be not prime? It means that it's a composite number. It's a composite. And if it's a composite, that means it can be divided into its primes. Okay? So it can be divided into primes. So maybe it can be. Maybe P can be written as, let's call it K times J, as two more numbers, okay? K times J, and so those are smaller numbers that multiply to give us P. So it's not prime, it can be divided into other things. Now, and these things themselves are prime, so maybe it can be divided into its primes. So here it's written as the product of primes. Okay? Well, here's the question. If these are primes, can either of those, K and J, can either of those be part of this list? Okay? What happens if P is divided by 7? What did we learn up here? If you take P and divide it by 7, what's going to happen? You're going to get this huge number, and you're going to get what? A 1 as a remainder. Agreed? What happens if P is divided by 17? You're going to get some big number, but you're going to get 1 as a remainder. What about 23? You're going to get a remainder of 1. What about 43? You're going to get a remainder of 1. No matter what prime number on this list that you divide P by, you're going to get a remainder of 1. So the point is, if you can write P as a product of primes, if you can write it as just a bunch of prime numbers that are all being multiplied by each other, maybe this is a better way to do it, it's a bunch of prime numbers that are all being multiplied by each other, P1, P2, P3, up to Pk, and they're all being multiplied by each other to give you P. That's possible, but the point is, all of these primes, none of them come from this list, because P can't be divided evenly by any of them, and so whatever these prime numbers are, they've got to be bigger than n. They've got to be over here yet, P1, P2, P3, P4, and so on. Okay, they've got to be larger than n. So in that case as well, n is not the largest prime. Okay, so either way, whether p is prime or not, we've shown that n is not the largest prime, which means that there is no largest prime, which means that there are an infinite number of primes that go on forever. So one of the most beautiful proofs in all of mathematics there. It's really kind of cool. Okay? So that's one thing we know about mathematics. Okay? About primes, I should say. There are a lot of other things about primes that we don't know. For example, look on this list right here. Notice that lots of them are paired up. They're paired up with one which is just exactly 2 more than it. Okay? Those are called twin primes. Okay? Twin primes have a neighbor which is just 1 away. Okay? There's the first one that doesn't have a neighbor that's really close. Okay? It's 6 away from this one and 4 away from this one. Okay? All these other ones are twins. The question is, how many pairs of twin primes are there? Are there an infinite number or just a finite number? How many? Infinite or finite? Go ahead, take a guess, and I'll tell you. You have your guess? The answer is, we don't know. No one knows. If you can prove one or the other, you will be instantly famous. Okay? You will be instantly famous. So you'll have your name on the fronts of newspapers. So you really will. This is a problem that's been around for as long as anyone knows, and no one knows the answer. Here's another one, which is just as interesting. If you take 4, you can write 4 as 2 plus 2. Take 6, you can write it as 3 plus 3. Take 8, you can write it as 3 plus 5. Take 10, you can write it as 5 plus 5, or as 3 plus 7. Take 12, you can write it as 5 plus 7. If you take 15, you can write it as, I'm sorry, not 15, 14. You can write it as 7 plus 7, or as 3 plus 11, right? If you take 16, you can write it as 5 plus 11, for example, okay? Or as 3 plus 13, as an example. What am I doing? I'm taking all the even numbers, and every even number I'm writing, at least in one way, as the sum of 2 prime numbers. See that? And the question is, this is called Goldbach's conjecture, because he was the first one who conjectured, who guessed, that every single even number can be written as the sum of 2 primes. And is that true or not? And it turns out this has been verified. We went up to 16. This has been verified for all numbers this big. This big. Not even sure the, let's see, million, billion, quadrillion, quintillion, sextillion. I think it's 4 sextillion. That many. It's been verified up to that big of a number, and yet no one has been able to prove that it's going to be true for everything. In mathematics, it's tantalizing that we have all this evidence that suggests that it's going to be true forever, but everyone agrees in mathematics, unless you prove it's true for all of them, you don't have a proof. And here's just something else just to show you why it's easy to come to the wrong conclusion. This is something that's in the textbook. If you take the polynomial p of n is equal to n squared minus 79n plus 1601, and you put a 1 into this equation, into this formula, put a 2 into it, put a 3 into it, no matter what number you put into it, you'll always get a prime number. When I say you'll always all the way up to 79. All the way up to 79, you'll get a prime number. So it's tantalizing again to think, oh, maybe this will always give you a prime number, but nope. As soon as you get to 80, then it fails. Then it no longer gives you a prime number. So it's real interesting that that you get things like that which work a long time, but then they suddenly fail. And so just because this has worked all the way up to 4 sectillion doesn't guarantee that it's going to work forever. And so that's still an open question. Okay, very good. Just a couple other things that are kind of important about primes. When you try to find big primes, which they try to do because we need them for security, one good way to find primes is to take 2 to a power and subtract 1. So 2 to the 15th, or 2 to the 10th, 2 to the 10th, subtract 1, that's 1024, minus 1 is 1023. That's a prime number. And if you do it for 2 to the 12th, 2 to the 12th minus 1 is equal to 2048 is 4096. Minus 1, that's going to be, did I do that right? 4, 4, 8, 6, minus 1. That's obviously not going to be a prime number if I did that right, because that can be divided by 5. Let's see. 2 to the 12th. Did I do that right? 2 to the 12th minus 1. So 2 to the 10th is 1024. 2 to the 11th is 2048. That's 2 to the 10th. That's 2 to the 11th. 2 to the 12th is what? Is multiply this by 2 and you're going to get 4096. So you take 4096 and you subtract 1, and obviously that's not a prime number. So the point is there are other ones as well. So they don't always give you numbers that are prime, but they often do. So it's a good place to look. So if you're looking for prime numbers, if you take 2 to some really, really big number and then you subtract 1 from it, you're not guaranteed that it's going to be prime, but it's quite no, I shouldn't even say quite likely, but it's possible. At least it's a good place to look. If you're going out west looking for gold, it's not that any place you look for it, you're expecting to find it, but you go to places that at least have a better chance than other places, and that's where you look. And if you're lucky, you'll find gold. And that's why there's a whole system now where if you want to, you can have your computer be a part of a whole community of computers that just looks for prime numbers from all these things. And every once in a while, some unknown person, they're the lucky one whose computer found it, and then again they get their name in the news. So anyway, cool. So that's all neat stuff. I think that's good. So we'll stop right there, and that's a lot of stuff about primes. Very good.